Hey class, so here's my second attempt at this video. I posted the first one accidentally having it have no audio, even though I talked through the whole thing. Apparently I was just talking to myself, but that's nothing new. So anyway, here's the second attempt at this video. This first problem here, it's an interesting question. We're told that we have some amount of gas that's at 300 Kelvin. Alright, so we have some initial temperature that's equal to 300 Kelvin. Alright, and then we're told we take the same gas that's in the same container and we heat it to 600 Kelvin. Alright, interesting. And we're told that its initial atmosphere, which is initial pressure, which is atmospheric pressure, is 100,000 pascals. Pascals are the SI unit for pressure, and we're asked to determine what its new pressure is at this second temperature, P2. So, the first thing that we might think is all we have is pressure and temperature. We're not told anything else. But we are actually told a little something else. We're told that we have basically a set quantity of gas in this container that keeps the same volume. So if you remember, density, the Greek letter rho equals density, is mass divided by volume. And so we have a constant mass and a constant volume. So the density is the same the whole time. And so you really have two options for going about solving this problem. One is you could use the ideal gas law, which I'll write out if you remember from class. P equals K, a constant number, which I gave you in class, multiplied by rho, the density, multiplied by T, the temperature. So one route would be to go ahead and solve the problem based on that, but there's actually an easier way, because what we can do is we can observe, as I mentioned earlier, the density here is constant, right? So that means these two values multiplied together do not change when the temperature changes. So what I will do is I'll divide both sides by the temperature to get that constant value by itself. So here my t's would cancel out, and so what we have is that our pressure divided by our temperature is equal to this K times rho value, which is just a constant. So I'm just going to say that's some constant. Alright? The cool thing about a constant number is it doesn't change. Alright? It's constant, as the name implies. So what that means is that P divided by T is going to be equal to some set constant value no matter what. Alright? Which what that means is that P1 divided by T1, let's say that constant is 10, it equals 10. Then P2 over T2 also equals 10. So if P1 over T1 equals the same thing that P2 over T2 equals, then P1 over T1 must be equal to P2 divided by T2. And so now you have this beautiful equation, which we'll talk about and use actually in a lab coming forward. But you can see you can easily solve for our unknown value P2 in this equation now that we know this relationship. Alright? So I'm going to leave that one part there for that question and move on to number 9, which is actually quite similar. Alright? Again, you're going to be using the ideal gas law. Alright, but you're just going to be using it in a slightly different way, because here we're told to be comparing the density, which is changing. It actually increases 40 times, and see how the pressure changes from that. So we have P1 is our same value here, 100,000 pascals. P2 is what we're trying to find. No, P2. Let me erase that. P2 is what we're trying to find, and we're told that we have information about our densities. Now we don't actually have a number for density, but we know that it increases 40 times. And because you're going to end up dividing them, all you need to do is just make up some unit. Let's call our initial one 1 unit. Okay, you can call it 1 Todd if you want, because that's a good unit name. Actually, that's a terrible unit name. We'll call it 1 Fox for George Fox. Anyway. And then your density 2 would be 40 times that, right? So we'll call it 40 Fox. You don't actually have to use Fox as your unit. But now you can do the same thing that we did before with the ideal gas law. P equals K rho T. And now K and T are your constants because we're told we stay at room temperature. So if you divide both sides by rho, what you end up with is P1 over rho 1 equals P2 over rho 2. And here you can see P is the pressure and rho is the Greek letter that represents the density. All right, so that's number 9, and then moving on to the last one, number 10 down here. All right, on this one it's a little bit of a different problem, but what's going on here is that you're asked to determine what the force is on a book based on its dimensions and knowing what atmospheric pressure is. So we're trying to find the force pushing on this book that just happens to be sitting on your table in your room right now, all right, or pushing down on your head as you read this, all right. This is a force that's being exerted on all things all the time on Earth by atmospheric pressure. So if you remember in class, we said pressure is equal to force divided by surface area. All right? So what is the surface area for a rectangular solid like a book? Well, surface area is just length multiplied by width. All right? But because we're looking using pascals and we're looking for force, which is usually in newtons, we need to make sure we're in our SI units, and so we need units of meters. So in this case, our surface area would be equal to the surface area of the book in meters. So 15 centimeters is 0.15 meters multiplied by the 30 centimeters, which would be, let me rewrite that, it would be 0.3. So I'm going to put the 0 in there just to make it a little more clear. So it would be 0.30 meters. And so you can multiply that together to get the surface area, and then doing a little algebra on our equation over here, if we multiply both sides by surface area, what you should find is that the force, F, is equal to the pressure multiplied by the surface area. Alright, so go ahead and try that one out, and you should be able to get all 3 of these, alright? So I think those are box worthy, and hopefully the audio worked and is box worthy this time as well. Hope you guys have a great night, and sorry about the fake out.